Good afternoon, sir. I am M. Manoj Kumar from EEE Department Section A. Today I am going to explain about a topic energy density in a magnetic field for CAA2. Energy density in a magnetic field. Definition. The amount of energy stored in a magnetic field per unit volume is known as energy density in a magnetic field. For the expression of energy density in a magnetic field, we have to consider the following data. Consider long solenoid having length L meters near the middle and the cross-section area A meter square. The solenoid is carrying a current I amperes through it. The volume associated with the length L will be A into L. The below diagram shows is the solenoid and in a magnetic field B bar of a length L meters. The magnetic field out of paper can be represented as dots, and the magnetic field B bar into the paper is represented as hyphens. The energy stored will be uniformly distributed within the volume as the magnetic field B bar is uniform everywhere inside the solenoid. Thus, the energy stored per unit volume in the magnetic field is given by small u suffix capital B is equals to capital U suffix capital B by capital A into small l, that is represented as equation 1. We know that energy stored in a magnetic field is given by capital U B is equals to half of L into I square. That means and it is substituted in the above formula in the equation 1. That capital UB is equals to half into L I square into 1 by A into L, and that is equals to capital L by small l into I square by 2a, and it is represented as equation 2. For a long solenoid, the inductance L per unit length is given by capital L by small l is equals to mu naught into n square into capital A. The equation 2 becomes small u capital suffix capital B is equals to mu naught into n square into capital A into I square by 2a, and that is equals to 1 by 2 into mu naught into n square into I square, and it is termed as equation 3. For a solenoid, the magnetic field at the interior points B is equals to mu naught into n into I. I is the current through the solenoid. The energy density in magnetic field is given by small u suffix B is equals to B square by 2 into mu naught. Mu naught means absolute permeability of a solenoid. And now I am going to solve a problem for CA2. The problem is a magnetic circuit comprising a toroid of 500 tons and an area of 6 cm square and mean radius of 15 centimeters and carries a current of 4 amperes. Find the reluctance and flux. Assume mu r is equals to 1. Mu r means the relative permeability is equals to 1. And the solution is the given points are number of tons n is equals to 500 and the area A is equals to 6 centimeter square, and it will be converted into meter square, that is 6 into 10 power minus 4 meter square. The mean radius small r is given as 15 centimeters and it will be converted into meters, that is equals to 0.15 meters. The current I is given as 4 amps. The relative permeability mu r is given as 1. The first we have to find the length of the magnetic path to find the reluctance. The length of the magnetic path small l is equals to 2 pi r. That is equals to 2 pi into 0.15. That is equals to 0.942 meters. The permeability mu is equals to mu naught into mu r. That is equals to 4 pi into 10 to the power of minus 7. And now we have to find the reluctance. First, the reluctance capital R is equals to L by mu into A. That is equals to 0.942 divided by 4 pi into 10 to the power of minus 7 into 6 into 10 to the power of minus 4. That is equals to 1.25 into 10 to the power of 8 ampere turns per Weber. The unit of reluctance is ampere turns per Weber. And to find the flux, we have to find the MMF. MMF is equals to N into I. That is equals to 500 into 4. That is equals to 2000 ampere turns. And now the formula for magnetic flux is MMF by reluctance. That is equals to 2000 by 1.25 into 10 to the power of 8. And the magnetic flux is equals to 5. The magnetic flux phi is equals to 1.6 into 10 to the power of minus 5 webers. Thank you, sir.